heard about this feedback-free starburst scenario in which the star formation efficiency at high redshift is very high. And this happens when the density is above a threshold, or the surface density is above a threshold. Now, the basic picture is that you have an outer generation of young clusters forming around 10 to the 6 solar mass, and they do it in a time that allows a feedback-free star formation burst. There are older generation of supernovae that generate wind. You have to be shielded against them. And you have about 10 generations during the period of the galaxy formation at cosmic dawn. You can predict the wind velocity and the properties of this gas and metals in them. Now, you might think that this efficient star formation will compete with black hole formation. And I want to speculate that this may not be the case. Actually, this setting of very many thousands of star clusters, like globular clusters, may give rise very efficiently to the growth of black holes the way we want them from the observations. So there are 4 elements you have to worry about that should work in those thousands of clusters. First of all, you can make 10 to the 4 solar mass black hole seeds by rapid core collapse in those clusters. And that's because they are young and rotating. I'll say a few words about it in a minute. You may end up with a high black hole to stellar mass ratio the way you want it, just because of those 2 features. Then the clouds disrupt. We'll hear about it in the next talk. And you can have black hole migration within the stellar disk of a very compact galaxy here, bringing them to the center in half a gigayear. And then you have to overcome the recoil during the black hole merger, which is a big problem, which may be overcome by wet compaction. So very quickly, this core collapse, there are 2 features in those very young clusters that may help you get a big stellar object which will become a black hole, the way Marta told me is going to happen. Now, the main new features here at redshift 10 are 2. First, it's a young cluster. So there are massive stars still alive during the FFB phase, and because of that, they migrate by 2-body interaction, actually, not dynamic friction, and you get a core collapse that's quite effective. Not effective enough unless you have a rotation in those clusters. Now, if those clusters are clouds that fragmented from a rotating disk, and we hear that those galaxies can be massive disks, then you have a so-called Gravo-Gyro instability introduced by Achisu in '79. And this is the fact that because of the rotating central region, you have speed up of the core collapse, maybe by an order of magnitude. At the end point, and you can't see it from some reason here, you end up with about 3 million years collapse. If the radius and the mass of the clusters obey of being below this purple line. So below this purple line of a radius of about 10 parsec and a mass of about 10 to the 6 solar mass here, you have a core collapse by less than 3 million years. And this is keeping the massive stars alive and the rotation giving you the extra boost. this is the density required for the FFB clusters. So the solution is that you can have a core collapse in 3 million years into a 10 to the 4 solar mass black hole if you are in a cluster of 10 to the 6 solar mass. This is a black hole of 10 to the 4. Now you'll hear about the quick growth from redshift 9 to redshift 4, 7 to get the high black hole mass to stellar mass ratio that you need, about 0.1. And the final slide is you need to overcome the recoil, gravitational wave recoil, in the mergers if you want to build the central black hole by mergers. Forgetting for a second the accretion that also will add up. You learn that if you're coming in a cold disk from the FFB disks, you end up with, you need a velocity of less than 200 kilometers per second in the escape velocity of the galaxy to retain the black hole in the middle. So that's going to work fine. If your disk is hotter, you have misaligned spins in the merging, and then you may need escape velocity of 100 kilometers per second to end up retaining the black hole. This can be a problem, which can be solved if you have compaction events that bring gas into the center and form a central bulge, because then the escape velocity can go high, and you may retain the black hole despite the very strong recoil. So these are all things to be studied properly, but in principle, having very efficient star formation at high redshift allows you to have those clusters that may give rise to very massive seed black holes that efficiently migrate inwards because of the compactness of the FFB disk, ending up with a central black hole that's growing mostly by mergers. This will be a low X-ray black holes because the accretion is not the major player in growing the black hole. Maybe it's going to give you the little red dots.